my name is Micah Silverman, and I'm a staff security hacker for Okta. Today, I'm going to be talking to you about hacking OAuth, Pitfalls and Remedies. And because we have a short amount of time together, about a half hour, I'm not going to go into great detail about OAuth and the flows. We'll touch on it, but it won't be as in-depth. But I have a lot of resources at the end, and that's what that QR code for is in the corner. If you're interested in seeing this slide deck or more resources on OAuth and OpenID Connect, go ahead and follow that QR code, and I'll show it again at the end as well. Now, for a quick little overview on OAuth, it's helpful to jump into a time machine and kind of look at the state of the art, say circa 2007. And this is an actual input form from Yelp. And it shows that in order to connect your Google contacts to Yelp, you had to put in your Google credentials. So in Yelp, you put in your email address and your Gmail password. Yelp would go and masquerade as you, grab all of your contacts, and then connect you with your friends. And they promise up and down that they don't keep your email password and they'll never spam you. But we have enough knowledge now from the lens of 2021 to see that there were all kinds of problems with this approach. The question that emerged was, how can I let a website access my data without giving that website my password for that data? We call this the delegated authorization problem. And it helps to have an analogy to relate to how OAuth works. And it turns out that how we interact with hotels relates to OAuth in some important ways. So with a hotel, we have these actors. We have the hotel guest, the hotel, the receptionist, and the hotel room. And at this point, it may be hard to remember, but we've all had interactions with hotels. So I go and book a room, I obtain a hotel key, and then I go to my room and I open the door. But it turns out that the way that we interact with hotels, this set of steps, which we in the OAuth world called a flow, the way that we interact with a hotel maps onto OAuth in some important ways. First, their scope. In the case of hotels, we don't really think of scope usually, but what it refers to is my hotel key will only open the room that's been assigned to me. I can't go up and down the hall opening just any old hotel room. That wouldn't be very secure. So the scope of my hotel key is limited to the room that's assigned to me. Likewise, in OAuth, we have an access token, and that access token can have scopes like read-only access to my contacts, for instance. The second way that hotels map onto OAuth is with expiration. If I leave the hotel and keep my key and come back the next day after I've checked out, that same key will no longer open the door because there's an expiration built right into the key. OAuth access tokens also have an expiration. And the third, and I would say most important thing to talk about is the notion of authorization versus authentication. Our hotel keys are what we refer to in OAuth as bearer tokens. That means that whoever is in possession of the key, if they know the hotel room, they can open the door just as well as I can. The hotel door isn't looking for my identity. It's not looking for Micah Silverman. It's looking to see that the key is valid, that it's not expired, and that it's meant for that room. And that's it. So I can hand my hotel key to my wife and she can open the door just as easily as I can. And this is the distinction between authorization and authentication. The door doesn't care who you are. And it's similar with OAuth. We have access tokens that are like the hotel key. They have limited scope and an expiration. And the entity that's going to be validating those keys doesn't care who I am. It's only checking to see if the key is valid, not expired, and intended for the service. So that brings us to some OAuth 2 specific terminology. The third column here are the elements that you'll find in the specification. And in the first column, we have the hotel analogy. And then in the second column, we have the roles, the actors that you'd find when using an app. So the resource owner, that's me sitting in front of my browser. I want a client app to do something on my behalf. So like Yelp is the client app, and me as a resource owner, I want Yelp to access my contacts on my behalf. Now, the client application needs authorization to interact with an API like the Contacts API on behalf of a user. And it's the authorization server that grants access in the form of tokens to an app. So the dance here is I grant access to Yelp to get an access token from Google in order to be able to interact with the Contacts API on my behalf. That brings us to the last element, our resource server. That entity has an API that an app can use if presented with a valid token. And again, the token has to be valid, not expired, and have the right scopes for the API. Other than that, the API isn't going to be concerned with the identity. So now instead of putting in my credentials when I go to Yelp, I see the friendly connect with Google button that we're probably all familiar with. And that kicks off this interaction between these actors. When I click on that connect with Google, it kicks off an interaction where I go and authenticate to Google. That's where I'm supposed to authenticate. So I never give my password to Yelp. Google gives an access token to Yelp. Yelp can then use that access token to go and interact with my contacts. For the rest of the talk, I'm going to review various OAuth flows that were originally created for different types of apps and different use cases, problems with those flows, and remedies for those problems. And where we're going to start is with the OAuth 2 implicit flow. This was originally created for SPA apps, for single page apps or JavaScript apps. And at the time, it was the best that we could do. There's always been problems with the implicit flow, but when it was first released, because of the restrictions of the browsers and because of the services that service providers offered, there were limitations on what we could do. So it was always problematic, but the good news is that now there are better ways. Now we're going to go through this very quickly, but this is how the implicit flow works. When I click on the friendly connect with Google button, it sends me over to the authorization server to authenticate. That's where I'm supposed to put my credentials in. From there, I get a consent form. It asks me if I want to allow Yelp to access my public profile and contacts in this case. And if I respond yes, it redirects to the browser with an access token directly. So we might imagine this is an Angular app, and the browser gets the access token, and now the browser can interact with the Contacts API on my behalf. Now, the short story of why this is problematic is because the access token is coming back directly in your browser's address bar, and there's all kinds of problems with that, problems with interception and reuse. And remember, the access tokens are bearer tokens. So once an access token gets leaked, then anybody can use that access token and masquerade as you or try to access APIs that they shouldn't have access to. So to demonstrate that, we're going to take a look at the implicit flow detector. This is a browser extension that I wrote. The link to it is available at the end if you follow the QR code. But it's a browser extension that detects websites that are using this deprecated flow, the implicit flow. And it so happens that not to pick on Medium because in fact there are a lot of sites that are still using the implicit flow, but Medium is one of them and it's easy to demonstrate. So I'm going to sign in. I'm going to use the friendly sign in with Google button. Now I'm already authenticated to Google, so it went back and forth with the redirect very quickly, but you can see over here that it now has me in an authenticated state. It knows who I am. Now, the problem here is that the implicit flow detector has been able to grab a hold of this access token. Now, why that's problematic is because that access token is intended for use with the Google API. And in fact, I can open up an incognito window here. So greenfield space, nothing up my sleeves, no session, anything like that. And I can go over to Google and use that access token directly. Let me show you what that looks like. I'm going to paste in a Google API endpoint, and this is OAuth 2 v1 token info access token. And I'm going to paste in the access token, the value of the access token that I got from the implicit flow detector. Now we can see that we got back all kinds of information from Google related to this access token. I have a user ID, maybe that's not so bad, but now the email address has been leaked. I can also see that the email is verified. Now this is in a completely private, no previous session established sort of environment here because I'm in an incognito window. So just by virtue of having that access token, I was able to get some information that I really shouldn't have had. And it's even worse than that. If I change token info to user info, I now get even more information. So I see the email address. We saw that before. I now have the full name. And I have a link to the user's profile picture, which Google does security by obscurity with that. So now you can see what I looked like in 1991. Maybe I didn't want that leaking out to the world. And you can get even more private information like the gender that I've set in my Google profile. So this is the bad side effect of leaking an access token. And the implicit flow makes it very easy to leak access tokens. So in order to get into the next flow, we need to take a look at the different types of clients that we can have. In the example that I gave with the implicit flow, we're imagining what we call a public client. Those are your JavaScript, your Angular, your SPA apps. They're your mobile apps, your native apps. And the key factor with a public client is that it's not safe to store a secret. So if I have an Angular SPA app, even if it's minified, developers and hackers can go and view source and extract strings and search through the code to find things like secrets. It's just not safe to store a secret. Confidential clients, on the other hand, those are your Node.js, Spring Boot, .NET applications that are running in an environment that's completely under your control. It's in your data center, behind your firewall. Doesn't matter if it's virtualized in Amazon or something like that. You have complete control over it. And in that case, that sort of client does have the ability to keep strings secret. Now, this business about keeping strings secret or not keeping strings secret, that ties into the next flow that we're going to look at, which is the authorization code flow. The authorization code flow addresses the issue that we had with the implicit flow, and that is the access token never passes through the browser's address bar. Let's take a look at how this flow works, and then we'll look at a vulnerability with this flow and how to mitigate that. So just like before, when I click on Connect with Google, I'm sent over to the authorization server. That's accounts.google.com to authenticate. I give my consent. Now here's where things get a little different with the implicit flow. At this point, Google responded back to the app with the access token directly. This time, it's redirecting back, but with this little bit of information called the authorization code. Now, the authorization code does pass through your browser's address bar, and it can be intercepted, but we're going to see in just a moment that that is not a problem in this case. So let's just imagine, as good security professionals, that this authorization code has been intercepted. Well, the authorization code has a couple of unique characteristics. One is that it's a one-time use code, and it has a very short window to use. With Okta, you have 30 seconds to use the authorization code before you have to start the flow all over again. Now, here's the key point. In order to use the authorization code, the only valid use of it is to exchange it for an access token. And in order to exchange it for the access token, you need the secret for the authorization server. So here's where let's say a malicious browser extension that's intercepted the authorization code gets foiled because that secret was issued by Google to your application and it's safely stored in that confidential client, let's say as an environment variable. So on your Spring Boot server, you have a client secret that's stored as an environment variable, and that's in your data center behind your firewall, inaccessible by the browser. So in order to exchange the authorization code, I need to pass along that client secret. And you may notice in the diagram, I have solid lines and dotted lines. The dotted lines are what we call a back channel of communication. If you notice, the browser is not involved at this point. Yelp.com, in this case, let's say it's a .NET app. So the .NET app is communicating directly with Google in order to exchange the authorization code for an access token. And this is a post request as opposed to a get request. And so that means the access token comes back on the same channel. And now Yelp.com's .NET application can use that access token to interact with the Contacts API with Google. The important point here is that the browser never sees the access token. All right, now this goes a long way to mitigating the problem that we had with the pure SPA app and the implicit flow, where the access token can no longer be intercepted. But there are particular types of attack on the authorization code flow, and one of them is called the authorization code injection attack, and that's what we're going to look at next. Now, with the authorization injection attack, we have some of the usual players that we've seen so far. We have a resource owner, an authorization server, and a confidential client. The key here is that a malicious browser extension has been installed on the resource owner's browser. We also have two additional actors. One is a centralized attack server, and the other is an attacker's computer. And the attacker also has a special browser extension. Now, you can already start to see that this attack is complex and it requires precise timing, and it's not easily done in the real world, but it is demonstratable by setting things up this way. Demonstratable? I think it's demonstrable. It is demonstrable by setting things up this way. So let's see what actually happens in the flow. So here I am sitting in front of my browser. I'm going to obtain an authorization code per the regular flow. So in this case, I'm interacting with a site called PaperCall, and I want to take a moment to acknowledge that PaperCall has done nothing wrong here. What we're going to see in a minute is that I'm tricking PaperCall into exchanging an authorization code from a different place. But I start out, I'm the rube, that is the resource owner, sitting in front of my computer with the malicious browser extension, and I get an authorization code per normal. Now, the malicious browser extension intercepts that code and doesn't allow the redirect to complete. Instead, it publishes that authorization code to our centralized attack server. Now, the attacker starts a normal authorization code flow as well. And this is important because of some of the security that's built into OAuth, in particular, the use of state, which is beyond the scope of what we're going to get into today. But the attacker's computer needs to kick off the flow as normal. Now, the redirect is also intercepted at the attacker's computer. And instead of allowing the redirect to complete right away, what it's going to do is grab that authorization code off of the attack server, and it's going to replace the authorization code that it got with the target user's authorization code. And then it's going to allow the redirect to continue. So the redirect gets back to PaperCall. PaperCall sees that the state is correct. It sees that there's an authorization code. And now PaperCall is going to exchange that authorization code for an access token. Now, to be clear, I haven't compromised PaperCall. I don't know the client secret, but I've tricked PaperCall into using its client secret to exchange the authorization code for an access token. And now that that's happened, the attacker's computer is effectively authenticated as the target. So let's take a look at this in action next. Let me jump over to another screen here, and there's a lot going on. It may be a little small, so let me describe what's happening here. At the top, we have our hacker dude, and this is Chrome, and to the right of that, we see the Chrome developer tools. Now, on the bottom left, we have our Rube dude. That's our target. And that's Firefox, just to show that there's nothing up my sleeve here. We're not sharing sessions or doing anything weird like that. And to the right of that, we see the Firefox developer tools. One thing I want to point out, if you notice up here, this is the public profile page for HackerDude and the public profile page for RubeDude. These are actual accounts that I created with PaperCall, and neither one of these are in an authenticated state at this point. This is just a publicly available profile page. Also, again, want to point out PaperCall is doing nothing wrong here. We're tricking it. And what gives us that leverage is the fact that our target, our Rube dude, has installed the Pretty Kitty browser extension. See, it shows you pretty pictures of cats. But behind the scenes, that Pretty Kitty browser extension is doing things like intercepting authorization codes and publishing it to our centralized attack server. The centralized attack server for this demonstration is a Spring Boot app. It's very simple. It just receives authorization codes and allows those authorization codes to be peeled off. So let's kick off the flow here. And to do that, I'm going to sign in. I'm going to click on Login, and I'm going to log in with Google. And I actually created Google accounts for these two users as well. So here I have, let's see if I can remember it. I think it's Rube. All right. Now, let's take a look at what happened here before we continue on. First of all, we can see that the browser extension intercepted an auth code and it published it to the centralized attack server. And now I'm in an authenticated state. So as an end user, I might think, well, that was strange, some kind of network hiccup. Let me just try to log in again. And now I'm logged in as the root dude. All right, now we're going to kick this off. And again, we only have a short amount of time to use that authorization code. Hopefully I didn't run out, but let's see. I'm going to log in with Google. And this also has its own account, which I have to spell right. All right, so over here, we can see that it intercepted my auth code. It replaced it with this other auth code, and now my hacker is in an authenticated state as the root. So the summary here is that the authorization code flow is very safe and secure. But the important thing is that it's only meant for confidential clients. We need a solution that'll work both for confidential and for public clients. And that brings us to our final topic, which is called the authorization code plus PXE. Now, we're not going to go into great detail about PXE. It's PKCE. It's pronounced PXE. It's an extension to OAuth that allows us to get all of the benefit of the authorization code flow for public clients. And the way that it pulls it off is by not having a fixed client secret, which, as we discussed before, is not safe for public clients. So let's see how this works in action. We have a sequence diagram here. If you're not familiar with sequence diagrams, it shows us the interaction of different actors over time, and we're going to follow the flow from left to right and top to bottom. So our lanes here are our resource owner, client app, and authorization server, just as we've had all along. Now, the resource owner is going to access the client app. Let's imagine this is the Yelp Angular app. And here's where things are a little bit different than the regular authorization code flow. This Angular app is going to immediately create a random value we'll call V, and it's going to take the hash of that random value using a common hashing algorithm, say SHA-256, and that result is going to be $sign. We're just using symbols to represent these different values. So this is already a difference. The app is doing some upfront work. Now the Angular app is going to redirect over to the authorization server, and it's going to pass along that hashed value with it. And the authorization server is going to store that hashed value for later. Now, if you haven't already figured it out, it's the combination of this random value and its hashed version that becomes a stand-in for a fixed client secret. This random value and its hash are calculated at the beginning of the flow every time. So even if you have a malicious browser extension or something else that is actively scanning for things like authorization codes, there's no way for it to know what this random value and its hash are going to be. Okay, so the authorization server stores the hash. Now it's going to redirect back, and now we're in the regular old authorization code flow. I submit my credentials to the authorization server. That's where they're supposed to go. The password completely bypasses the Angular app. That's what's supposed to happen. And the authorization server, like Google, is going to authenticate me, and it's going to redirect back with an authorization code. So far, this is just the regular authorization code flow. Now the Angular app has its hot little hands on the authorization code, and let's imagine that a malicious browser extension like the Pretty Kitty extension has intercepted that authorization code as well. Now here's where that malicious browser extension is foiled. The client app, our Angular app, exchanges the authorization code for an access token using that original random value that it created at the top of the flow. The authorization server validates the request by looking at the authorization code, making sure that it's not expired, and it takes the hash of that random value V that was passed to it, and it compares it to the hash that it stored earlier. Assuming that matches, then it will return a token, and that access token comes back on the back channel, the result of a post request. And so that access token never passes through the browser's address bar, even though it's coming back to, in my example, an Angular app. So this is kind of a whirlwind tour of Pixie. There's a lot more to it. You'll see more resources in the GitHub repo, which I'll show the QR code for at the end. But as our last demo, let's look at the Pixie flow in action now. So to do that, I'm going to jump way over here, and first thing I'm going to do is exit my backend server from the injection flow that we just saw before. And I have this project called the Pixie CLI. It's written in Node.js, and it simulates a native client. And all you need to pass it is a valid Okta org and a client ID. And just as an aside, quick shameless plug for Okta, you can go to developer.okta.com and create a free org that includes access to OAuth as a service, OpenID Connect as a service, and then you'd be able to run this Pixie CLI example yourself. All right, first thing it does, it creates the code verifier. That is the random value V that we saw in the diagram. It also takes the hash of that random value and it base64 URL encodes that to give us our $sign value, the hashed value. Then it's going to call the authorization server and it passes in a whole bunch of query parameters, but importantly, it passes in this code challenge method and the code challenge. And the code challenge is the hashed value. So even though this is passing through the browser's address bar, by virtue of the way that one-way hashes work, there's no practical way to reverse this and get the original random value V. All right, now this is going to launch the browser, and it's going to give me an opportunity to sign in here. Now I'm at the authorization server. In this case, it's Okta. I'm going to go ahead and authenticate here, and it's going to redirect me back, and it's telling me that I can close this tab. Notice up here that in the browser's address bar, I have the authorization code. Let me kill that. And now we can see that my native app here, my Pixie CLI app, has intercepted the authorization code. That's what it's supposed to do. Now I have 30 seconds to use this authorization code, so let's see what's going to happen next. Next thing it's going to do is it's going to post to the token endpoint, and it's going to pass in the code that it just got, and it's also going to pass in the original random value V. It's going to pass all of that to the token endpoint. And what the part that we don't see is that Okta is going to hash this code verifier, and it's going to compare it to the code challenge that it stored earlier. Assuming that all checks out, which it does, an access token is returned. And the last thing that the Pixie CLI does is it validates, it uses that access token to hit a protected endpoint just to prove that it's a valid access token. And user info gives me some more information about the user. So that's the Pixie CLI in action. And this using the authorization code flow with Pixie is suitable both for confidential clients and for public clients, and it addresses all of the issues that we saw with the implicit flow and with the authorization code flow without Pixie. So here once again is the QR code that you can use to get this slide deck and all of the references and links to the code. You can at me on Twitter at @afitnerd. You can at our developer advocacy team at OctaDev. And if you go to developer.okta.com, you can create a free forever Okta org, which includes the OAuth and OpenID Connect as a service. I hope you found this useful and instructive, maybe even a little fun, and feel free to contact me. I'll speak to you soon.